Okay. So I guess we will start again. Maybe, yeah, any more questions of what we covered so far that you may have thought of during the break that we can hit before we jump into the input files and guidance? Anything by group today, but okay. Yeah, so this section is really about, I guess Emmanuel showed you briefly what the input file looks like. We'll step through that a bit more and really provide some guidance. On settings, this is mostly for gut feel, so you have a sense of what these things should be. Again, I think the toolbox does a lot of the stuff for you, so you don't necessarily memorize all these things, but hopefully this gives you a sense of what the toolbox is doing in the background. So first of all, obviously you've seen the input file now. Again, it looks exactly like an OpenFast file with the 3 columns, where the only real column that matters is that first column, which has the actual setting. The second column is really the name, really the keyword we use for all our documentation. And if you search the source code, you'll also find that keyword. So if you need to dig in, figure out what it's doing, you can search that keyword. Then the rest is just comments. Again, just like a mini user's guide sort of comment there. The only thing that really matters when you run FAST.Farm is the first column. So yeah, a couple things as we go down here. So first of all, so Tmax here is in FAST.Farm. Obviously, you know it's in OpenFast as well, and just keep in mind that this will overwrite whatever is in the OpenFast model, so you don't need to change it there as well, but this will simply overwrite what it's doing. Yeah, the next option is the mod am_wind, and yeah, this actually may be changing here in the next few months as we're talking about hybrid inflow and so on options. But right now it's 3 options. Option 1 is you're using LES precursor, and right now that precursor stores a VTK file directly that FAST.Farm can read. The other 2 are really for the synthetic models, and there's mod_wind 2 and mod_wind 3, and mod_wind 2 is really just saying there's one inflow wind instance that is used for both domains. Generally not recommended, because we generally recommend having different discretizations in the different domains, and this would be the same effectively, one terpsim for all. So actually that option may be deprecated here pretty soon, because we generally don't recommend ever using it. But yeah, so it's really 1 and 3 we want. The 3 is really, again, multiple instances of inflow wind. So the low res has its own inflow wind instance, and every high res has its own inflow wind instance, which means you need like a terpsim file for every domain. And the big question there is, how do you make sure the flow is consistent between the different boxes? And the script, again, will set that up for you using this time SR feature. So there's that mod am_wind. Wave field, this is really if you have an offshore system, and question comes, does my wave propagate through the farm consistently or not? Yeah, you have a question? Sorry.
Yeah, quick question. So you probably mentioned at some point, where would you typically get your LES, your hybrid LES, like where does that come from typically?
So we would generally at NRoute be running AMR_wind for that. So that's our structured grid large eddy simulation solver.
Do you do it per case? Is it some precursor wind that's just there for field that you plug it with?
We've done it both ways in terms of per case or not. If the size, obviously the thing you have to keep in mind is make sure if the farm has to fit in it, turbine has to fit in. So if I using the same box for a 5 megawatt or 15, probably not going to work. But if I have my 15 and I change it to a 15.5, it's probably still good, and you can keep it in the same box. So yeah, it's kind of like terpsim that way, right? Usually you run more OpenFast simulations than you do terpsim runs. It's the same idea here. We can reuse it as long as the farm and the turbine fit in the box.
Is that a benefit? But considering that you're probably going to use a tool that will not require such high fidelity.
benefit to reuse, or
What I'm trying to say is like, if I took the tool already, lower fidelity, and very high fidelity.
yeah, the big idea here is that, yeah, it's maybe large eddy simulation, but it's pretty coarse large eddy simulation. Like you don't need the resolution that a turbine would need. Like usually if you're doing a turbine, you need, sub-meter scale and it's very small time steps. We don't need that scale here. So, we need, low res, we need 20, 30 meter scale. We'll talk about discretization requirements, but it's pretty coarse. And you do need the high res box. You need to get down finer, but definitely not to a large, like an actual line simulation. Like you need chord scale, not sub-meter scale. So it's LES, but it's much coarser than a turbine simulation. Right. And you can, like I said, reuse it for other cases. So it's that same inflow, I can do lots of things. So that's the, otherwise, yeah, why is it? And then the other thing is, again, we're moving in the future towards a more hybrid inflow, and then you only need the coarse one, and that's really efficient. So yeah, so going back to the mod wave field again, really there's two options there. One is completely independent waves at every turbine, maybe not that useful. Mod win 2, make sure that wave gets propagated through the farm consistently. So that's probably the one you generally want to use, and that basically shares the random numbers and uses the dispersion relationship to propagate that field. Okay, now getting into the domains again. So first example was making sure the box fits the domain. So first of all, a little bit about time steps that we recommend. Again, the toolbox will do this math for you. But these are generally the rules of thumb for high domain, or the low res domain DT and the high res domain DT. So first of all, for low res, you see, first of all, it scales with the diameter, which makes sense. The bigger turbine, the bigger the spacing can be. It's inversely related to the hub height wind speed, which means, for really low wind speeds where the flow is slow, the time stack could be very large. Really high wind speeds where it's moving quick, time step is smaller. And you see that there. So for the NREL 5 megawatt, that's, like for rated, it's probably 2 or 3 seconds at rated. For DT low, at 18 meters a second, you're probably down to a second. And at cut in wind speed, it's maybe 5 or 6 seconds. So it's that sort of relationship we're talking about. And then DT high, we usually tie that to how much frequency content do you want? Do you want 3P? Do you want 6P? Do you want 9P? 1 over 2 times that is basically the rule of thumb. So usually I would say 9P or something would probably be sufficient for elastic solve. But there's some numbers there. C meander is roughly 2. Wake diameter is roughly the rotor diameter, and that will give you nice numbers for those formulas. FAST.Farm already requires a couple other things. Let's see, the curled wake. We say, yeah, maybe it's slightly smaller than that. Our experience has been to not really as strict as what original guidance was, because we were in cases coarser. Like we accidentally didn't follow the guidance and it was still stable. So, but nevertheless, the curled wake may require some smaller time step than that. DT high is generally, quite a bit smaller than DT low. And right now we just require that they be an integer divisor of them. So it subsamples easily. And likewise, DT of OpenFast, usually quite a bit smaller than that even. Again, must be an integer divisor of that. Yeah, when you do the LES precursor, right now it dumps all this VTK data from the LES, and you basically just give the path to those files. That's all that is. We are changing the VTK option to be more direct AMR wind output. It's a binary output, but much more efficient here soon in the future. But right now it's the VTKs. So now get down to the spatial resolution. So yeah, we need to find the spatial resolution box. Again, Emmanuel said you give it the origin, you give it the spacing, you give it the number of points. Really hard to set up manually, but toolbox will be basically using this rule of thumb here. There's a couple things in there. So one is, again, this scales with the diameter, which makes sense. It also scales with the wind speed. And so you can imagine and this is now V hub is in the top. So as your, higher wind speeds, your time step is dropping, but your spatial resolution's getting bigger. So overall, it tends to be very similar memory requirements for both. Yeah, so low wind speeds is very big time steps with smaller spatial scales, just because things happen quicker and things move slower. So there's the rules of thumb. If you plug in the previous equation for DT low, you see that in there as well. If you want that, but yeah, that's the relationship. And this is true for anything, whether X, Y, or Z, effectively the same rules of thumb apply. I have that last bullet there about NANs, and this comes in. Yeah, we have a little hack in there right now. So right now, the domains are fully rectangular always. And if you have some complex terrain where there's a hill, say in the middle of the terrain, what do we do with it? Right now, we have basically a NAN option, whereas if you define any velocity, in that rectangular domain, if any of the velocities is given a NAN, we say that's below the ground. And basically FAST.Farm ignores that point in the solve. So it traps the NAN and treats it as a boundary in the flow. We use that again if it LES precursor with a hill, use that option for that to do wind farms with complex terrain. Let's see. So yeah, when you say you want mod m wind free, this is where you give the name of your inflow wind input file, and here's some general recommendations for TerpSim or MON inputs. Generally recommend that the inflow be fully periodic. That's an option in TerpSim, and also it's automatic in MON. Meaning, like in time, it's time zero and time end are the same, so it can run it periodically through, and that's basically extends the domain infinitely in the X direction, which is pretty nice. So we generally recommend you do that. Next one is really pretty critical. You want to make sure you align the TerpSim grid with the FAST.Farm domains, meaning point to point matching. You can skip points if you don't want full resolution, but you do want them to align. If they don't align, FAST.Farm will simply interpolate from the TerpSim domain to the FAST.Farm domain, and that sounds great. It's just and that's what original thought was we don't need to align them. We can just have them independent. We just interpolate. And it does work. It does interpolate, but what we found out the interpolation does is smooth out the turbulence of it. So if you're inputting TerpSim at 10% TI and your grid points are halfway in between them, interpolates it in. Effectively, FAST.Farm will see it as a 10 or 8% TI, with 10 to 8, just because the interpolation will smooth it out. And that's been a big sticking point. And so now we always recommend you basically just align them. And right now, again, it's a little annoying because the user has to specify it here and they have to specify it on the TerpSim side and make sure they're consistent. Really hard to do by hand, but the toolbox, again, will do that for you. That next bullet, again, is also for the same reason. I'm talking during the break about this. So right now in inflow wind, you can say my propagation direction is 10 degrees or 20 and use that to say rotate the wind field. But again, because you're trying to align the domains, you can't really do it that way. So yeah, we generally just use zero direction. And if we want to have different directions of our farm, we have to rotate the whole farm. So that's a bit annoying. Not the same requirement for LES input, but if TerpSim, that would be the requirement there. They basically can try to align the grid. Importance of transverse coherence. This is mostly just a warning, and the documentation provides a bit more guidance there. But some of the defaults in TerpSim are to say there's no transverse coherence of the flow. And if you have that default turned on, then effectively there's no wake meandering either, because all the Y and Z grids have completely random. There's no continuity at all, the flow. And the FAST.Farm is a spatial average, and it averages away, and you never get any meandering out. So yeah, when you generate terpsim inflow, make sure your transverse coherence is turned on. Yeah, hub height, grid height issue in terpsim, that's a little bit of a detail. Normally, if you're doing terpsim for like the big low res domain, your box is quite a bit higher than the turbine. And so, yeah, unfortunately, terpsim calls the center of the grid the hub height, and that doesn't necessarily not really true for a FAST.Farm model. And so there's an issue on that we post, but yeah, it's mostly a warning. Terpsim, you have to interpret a little bit differently because the hub height is not necessarily the hub height for FAST.Farm. And MANA has a similar issue with X and time. That was posted. There's an issue on that too, but I won't jump into that here. Okay, so there's some guidance there. Let's see the next section, NAWEA file. I think you've seen this already in manuals example 0, but yeah, next section, you see the wind turbines there. This is showing just one example of one turbine with the high-res domain grid there. Then we have the wake inputs and some wake out of turbulence settings. We'll jump through those a bit. Again, that when you set up your model, you say where your turbines are. So each turbine has an XYZ location. Z is really there if you do complex terrain, for example. Let's see. Every OpenFast model needs its own input file given there. So every turbine needs its own OpenFast file. And again, if you're using a bladed style controller, the way it works is you need a copy of that DLL or .so file for every turbine you have, because there's actually data stored in that DLL that's not dynamically allocatable, which is really a limitation of the DLL. So right now, if you have 10 turbines and you're using Rosco or any bladed style controller, you need to make 10 copies. So just make the one DLL and copy it 10 times, rename them all. Because they all have different names. That means your server dynamic file has a different name. And then your OpenFast file has a different name. So yeah, it's a little annoying. Again, the toolbox will handle this all for you. But yeah, so usually it's every turbine will be given its own input file, even if it's exactly the same turbine. Really because of that Rosco limitation or Discon limitation. Then the high resolution domain, again, this domain, and you want to extend around the turbine, and that considers any displacement you'd want to guess. So, if it's land-based turbine, you pretty much know where the turbine is going to be. If it's floating, you kind of have to guess how much it's going to float in different directions and make your box that size. And then for the resolution of that domain, we typically say max board, and we've done some conversion studies on that before. So for the NREL 5 megawatt, it's about 5 meters. For the IA 15, that's about 8 meters or so. That's for the spatial resolution you want there. I forgot to mention earlier, this slide, missed that first bullet. Low res domain, how big of a box you want. Generally, we recommend a 3D gap, between the turbines and the edges of the domain. And that's really to account for the meandering of that wake. So both horizontally and vertically, just add 3 extra rotor diameters of distance to capture the wake deflection and meandering behind, except downstream. So the wakes can just leave. If the wakes hit the boundary, they effectively just leave the domain and never come back. And so that's fine downstream, like let the wakes leave, you don't care. But on the sides and the top, yeah, definitely add that 3D buffer or you'll definitely miss something, because the wakes will kind of meander and they'll probably meander outside the domain. And that's not going to be a good answer at the end. So for the turbine, like I said, just want it around the turbine, including whatever deflection of that turbine you expect. You just have to guess that ahead of time. Let's see, so we went through that. Let's see, now we get to the wake dynamics section. Mentioned there's really the 2 models, there's the polar and the curl. We actually added a third option, which is Cartesian, which is really just the curl without the vortices shed. It basically gives the same answer as polar. but it's more expensive, so I'm not sure why you'd ever use it, but it was nice for debugging purposes. So the two options there, polar and curl, and yeah, we're changing the curl one right now to be a better formulation, but those are what you got. Next section is the definition of the wake planes themselves. So again, there's two things to do there: is how many planes and what's the discretization of the plane itself. So for the DR, we recommend about, whatever that rotor diameter is, over 15. That's probably a good size for DR. So for the interval 5 megawatt, that's DR of 10 meters or something. And then the number of radii, say 3.3 the rotor diameter over DR, that's the radius. So it's like basically saying we want the plane to be about 3 times the diameter of the rotor. And that's really to capture that, wider domain. And that's because of that jink function we're weighting the plane with for our spatial averaging. We want it wide enough to capture that weighting function. So that's where that comes from. So about 3 times the rotor diameter is the diameter of that plane. And then the number of planes, here you can see the math. It's how much distance downstream you want it to propagate. Is it 10D? Is it 15D? Is it 20D? Divided by the time step and say the propagation speed of the wake. And if I plug in my DT low from the previous formula there, I have the second equation, which is actually pretty interesting because it basically says it doesn't scale with the spacing at all. It doesn't scale with the time step. It's just a constant. And it's usually about 140, 150 planes. And that's usually sufficient for basically any case. As long as you're scaling DT following the rules of thumb, that would be correct for that. So this one doesn't really change with wind speed, as long as you follow the rules of thumb for everything else. We are changing this one as well. Don't have it in the slide, but mentioned previously, we're talking about this regions of wake influence value, where it goes from the n squared to the n log n math on the calculation. And when we're doing that, we're actually changing this input. So instead of inputting number of planes, you're basically going to input that distance. So give me 20D, don't go beyond that, and that will be the input coming probably in version 5. And it makes a lot more intuitive sense, I think, than this number, although this number's been pretty constant. Anyways, that's coming soon. And this is what you have now. Let's see. Yeah, the next set of parameters is everything tied to these sort of 20 or so parameters that you could calibrate better or not for a given large simulation case, say. These 4 parameters here are for this wake deflection correction. Generally, I don't like this model at all. This actually matched what used to be in Flores. And I think Flores phased it out, so we'll probably phase it out here at some point too. But yeah, these just give a little nudge. You see, this is showing a case where there's a yaw error, and that yaw error leads to some wake deflection. Yeah, this basically adds some mean correction to that, some linear correction relative to what it would have done otherwise. So don't really like it. I think it meant to capture things like a Coriolis term or something that's missing in the solve, but I think with our curled wake model, it basically eliminates the need for this correction. These K values, these are the values that show up in the eddy viscosity model, and there's 5 for each term. They give this ambient wind term and the wake shear term. Those are the 2 sets of parameters. Each one has a set of 5. They basically define some function that looks like that, that you can calibrate them to match what the LES is doing at different downstream distances. Those are what the defaults are for those functions. But again, if you had better LES solutions or you wanted to match something else, you can calibrate these to those solutions. We talked about those functions, and that's basically determined by this mod meander and C meander switch, what those functions look like. Next is in the curled wake section. Again, this is probably change once Emmanuel's new work is done. Right now, there's probably not much you need to do here. Number of vortices is like how many horseshoe vortices you're adding to the wake. Generally, the default's fine. The only ones that you may be able to find some sensitivity to are this K vortex decay and KV curl, which go into this eddy viscosity formulation again. So you could calibrate those to a given case if you had some data to calibrate against. But for the most part, we've found these defaults pretty good. Finally, we have the wake added turbulence section. Yeah, it's pretty nice actually. We give you a predefined isotropic turbulence box for the background turbulence, and I've never seen a need to not use that one. Like, I think you could use that over and over again. It's probably fine. But if you have your own, you can replace it. And then, yeah, really the two things that really matter here are this watt K depth and K grad. These are the two terms that affect how much the wake added turbulence comes from the deficit itself versus the gradient of the deficit. And you can see the calibrated functions we ended up putting in there. Those dash lines sort of fitting the LES data that we had. And yeah, again, haven't had a need to change them since our calibration step, but if you had good data to calibrate against, you could feasibly calibrate those again for your case. How to generate this box?
Yeah.
It's basically an option. It's basically we ran the DTU model. It's just a mon box, and set up there's really only 3 inputs in that box, and we set it up so that you get isotropic turbulence out of it. So, but yeah, the same box applies to any wind speed, any size. So it's pretty nice. We simply scale it around. New as in, yeah, maybe a year and a half ago or something. It's been there for a while now, but yeah, it was new. Torque last year, we presented that, so 2024. Last section of the input file is really just about visualization and output. Top option there is probably not recommended ever to be true. It basically dumps the full high res and low res domain every time step. That would be very useful for interrogation of what's going on, but yeah, it'd be a lot of data, so we never turn that on for general use. But if you really want to see what's going on, you can turn that on. Normally what we would do, again, not for every case, but once you start want to understand what's going on, visualize a certain case, you add these little strips, which are basically cut planes through the flow. So you can do vertical in the 2 directions, as well as a horizontal slice, and place as many of them as you want. These are just showing you some places you could use as examples there. You don't need to output it. It's kind of calculated internally anyways, but just useful for visualization purposes. The rest of the sections, what gets written to the file at the end of the day. Mostly what we care about is what OpenFast outputs. How's the turbine responding? So yeah, that's not here. That's back in the OpenFast file. But yeah, really, this is really about interrogating the wake characteristics and so on. Yeah, any questions on input files or guidance before we jump into the examples? Yeah.
The input file reads the 13 BTX file. The bigger file. I think once I was trying FAST.Farm, and I had an issue. So my question is that 13 file, is it the one that is taken as the input of the first turbine? And is it possible to have different inflow files for different 13 files?
Yeah, let's let me just jump back here. Let's see. Maybe I'll first say, where did I say that? So again, there's three options. Oops. So yeah, mod AMN2 means there's one terpsim file for the whole domain. Mod AMN3 is their separate ones. Maybe I'll just jump back here to explain what that means. Yeah, so mod AMN2, again, there's one file for the whole domain, which naturally means the low res and the high res have to have the same visualization because it's one file. Again, that goes against all my rules of thumb I just explained to you. But so we generally don't recommend using that option. But mod AMN3 says, yeah, the low res and the high res will have different terpsim files. And so the next question is, well, how do I get my high res to match my low res? Because I want that to be the same flow and not independent. And so the trick we use for that is this time SR feature of terpsim, which basically says we first generate the low res. So there's my low res domain. It's done. I have terpsim for that. And now I sample that domain at the points of where the turbines are. And I use that as an input to my second terpsim domain, the high res domain. And I basically constrain my high res box to match that low res box. And that's how we solve that problem. So when you use mod AMN3, that's what you're doing, is you're constraining the high res to match the low res. I first solved in low res. That makes sense? Yep. Any other questions on the input file? Or let's jump right into examples. Yeah.
So you mentioned some of the early table text again.
Yep.
So I have some tunnel data, hardware conversions. Would that be adequate, or what do you think is the scale of data that you need to comfortably fit those parameters?
Yeah, I mean, usually we're trying to calibrate things like the lake deficit at, say, different distances downstream. So if you're, some PIV or something where you're hot wire, maybe I don't know how many hot wires you have, but yeah, for 1 point, maybe a little hard. But if you have some PIV where you can really measure a lake deficit as a function of distance, that would be useful. And you could definitely use that to calibrate against. But yeah, hot wire point measurement, I see lots of them. Any other questions? I mean, maybe the challenge there, of course, is the wind tunnel is not necessarily giving the right atmospheric boundary layer. Depends on your wind tunnel, I guess. But yeah, if it's if you're aiming for purely smooth flow, then okay, well that's nice. So again, often wind tunnels are like idealistic, and then maybe that's not the best calibration data, but yeah.
Yeah,
I see. So yeah, you could sample it differently and then average it out and make sure that on average it's good. When we do it on LES, usually what we try to do is we look at a full cross cut plane. So it's like a PIV measurement of the LES, and then we'll post process that and figure out, how's it meandered? Where's the wake center? What's the deficit in the meandering frame of reference? And then we calibrate to that, and that's it's feel like it's easier in the sense that we can basically really match what FAST.Farm is going. So yeah, you would probably need a PIV in the tunnel to do that. Yeah, anything else? Okay. Yeah, Manuel.
So more examples. We're going to try now. So as you can see, the OpenFast input file, there's a lot of inputs and you can easily set them wrong. So if you are to use FAST.Farm, you're going to enjoy using the toolbox, or you kind of have to use it because it gets so complicated. Hopefully we're all set with example 0 at this stage. And example 1 is actually not too bad. It's just trying to figure out what is the discretization, what is the delta S, delta T that you need. And Jason showed you some formula. It depends on the chord max, on the rotor diameter, on the meandering, how much your wake is meandering sidewise, the frequencies of your turbine. Jason mentioned 9P, the hub height. Unfortunately, it depends on which wake model you use. So you have the polar wake and the curled wake. The curled wake, as Jason said, you need a small time step and a large spatial discretization. In this example, I'm using mode wake equals 1, which is the polar wake, because I tried to make an example for you that runs quickly. Otherwise, the time steps get a bit too small and the examples are a bit slower. Anyway, and of course, it depends if you're using inflow type is going to be, are you using TurboSim or LES, basically. So you'll find those parameters here in this cell. Like, what is my chord max? This is for the 15 megawatt. Actually, the chord is pretty small for the 15 megawatt, the max chord, because it is transportable. So 5.5 meters is the max chord. Frequency max, it's going to affect your delta T high. Again, in that case, I think we are being conservative in that example, so that's okay. Hub height, simple parameters like this. And those parameters that are defined here, they somehow for the toolbox, they are defined per turbine if you want. So we're going to put 2 turbines in our wind farm. And because I want the simulation to run fast, I place them 2 diameters apart. Jason showed you the XYZ coordinates of the turbines. And so if you run this, you'll see how they look like. That's the plot FAST.Farm setup. By the way, this function plot FAST.Farm setup can take all kind of first input. You can give it an input file, you can give it an object, or you can give it a dictionary of wind turbines. In that case, you don't have any high res or low res. It doesn't know it, so it just plots the wind turbines. And you can see they're very close to each other and slightly staggered. And the question is, like, how do we need to set up our delta S, delta T? Again, we depend on mode wake, and I'm using mode wake 1 because it's a bit faster to run than the curl wake. Inflow type is going to be TurboSim. We don't have any LES. No one here has run LES. We're going to use TurboSim to generate the turbulence box. Hub height is 8 meters per second. And said hub height shows up at the bottom. So whatever. And that it's going to depend. You can have different resolution based on the wind speed. And then comes this massive class. If you know Python, this is a class, FAST.Farm case creation. That takes a zillion number of parameters. But right now, we're just giving it the minimum number of parameters possible, the wind turbines, the hub, which wake model are we using, and the fact that we're using TurboSim. If you run this cell, it should tell you a couple of messages, a bunch of information. First of all, it tells you, well, you didn't give me the temporal and spatial resolution. That's true because we don't know how to set them up. So we're basically asking the class to tell us. When we don't give this as an option, the class tells us, okay, I'm going to try to set the ES low to be greater than 25 meters. So you can see it's quite big. The low spatial resolution is quite big. But then in that case, internally it compute that it needs, it knows the high res needs to be about 5 meters. It computed based on the guidelines. The high resolution is 5 meters. And in that case, it tried to find a multiple integer to match so that the low resolution is 4 times the high resolution in terms of spatial resolution. That's based on the guidelines, all the equations that Jason showed you. So at the end, it tells you what is the delta T high, what is the delta S high that the toolbox recommends you to use. So it's a good first approximation. Okay, 5 meters of delta S high, 20 meters of delta S low. And then we can plot our layout. And unfortunately, this doesn't plot the grid. It's a different function. It just shows you how big is the domain that automatically using the guidelines, probably 3 diameters on each side. And then it put a box. As you can see, the 2 boxes are pretty close to each other. Those 2 turbines are very close to each other. You're getting an error? Yeah, who gets an error? What is the error? Let me see. That's great. Why would you type it in? Whoa, look at that. That's cool. XR. Ah, X-array. Oh yeah. So you need a pip install X-array.
Yeah, I tried to do that.
And it failed.
I did have a minute.
Yeah, so unfortunately, my colleague Regis that took over the toolbox loves X-arrays, and you need to pip install X-array, and that's unfortunate. For you, you have it, but yeah. So ideally, you need to do this or Python-M, Python-M, pip install X-array. And yeah, you need X-array to run a lot of things, and even though like it's not really needed here, and but yeah, that's a bummer. I hope that's gonna work for you guys. Otherwise, well, you're gonna be a bit stuck. Who is stuck with the X-array? Raise your hand. It's Jason. Yeah. Can you try? Can you do pip? Do you have access to pip? Okay, so hopefully that's gonna work, and you don't need to restart anything. Hopefully Python knows that you have X-array. Oh, yeah, turbine line. And so if you had more turbines, like 6 turbines, it shows you the box where the turbines are. What's your question? Yeah. Yeah. We haven't so far we haven't reset the inflow, so the inflow by default is gonna come a 0-degree angle. Yeah, just think of it. It doesn't mean much right now. Forget about it. It's just it drew a line between the turbines. If you had multiple turbines, it's gonna draw a box around the turbines. It's not very interesting. It's nice when you actually rotate the turbine. There's like a special case, and you can see the line moving a bit. So we are engineers. Sometimes you know what you want. Ideally, you do the calculation yourself, and you're like, okay, if you remember above, it said 24.32 meters would be what the guideline would say, and instead it picked 20 meters. 24 is close to 25, so let's just say DS low should be 25 meters. So that's what happened here. So now we know DS low should be 25 meters, and we give it as an extra input to this big class. And we rerun it, and now the class is going to try to respect whatever we want. And you can see it respects the low resolution is delta S low 25 meters instead of 20 meters. And you can do this once you understand what the class tells you and what you do with maybe your hand calculation. You can try to also like set up all of those parameters, and then you run the class directly. And it tries to apply as much guideline as possible, but it also respects your inputs. Yeah. So DSLO, sorry, I'm going to scroll up. The first time I run that class, sorry, I need to scroll up. The first time I run it, I didn't give anything, and the guideline said, well, the guideline is not really respected, basically. That's what's going on here. The guideline said DSLO should be 24.32, and instead they picked, there's like an integer problem here. Instead of being conservative, the toolbox is not being conservative. Well, actually, no, it's being conservative. I'm sorry, my bad. It is being conservative. So it's using a smaller delta X if you want. But as engineers, well, okay, let's violate the guideline between 24 and 25. Let's just choose 25. It's going to run faster. So that's the kind of thing you can do. Of course, you can. It's better to use the recommendation as much as you can. And in that example, I'm not going to use the recommendation too much. I'm going to like stretch them a tiny bit because I want the cases to run fast for you, to run quickly. So yeah, you can pass those parameters to the class. And that's about it for example 1. Example 1 is about finding how big is my domain based on my wind speed, my type of wake, my chord max, my frequency max. How do I find those delta T and delta X? And we are manipulating an object which is called a FAST.Farm case creation. And at any case, you can print that object and it tells you also a bunch of information about the simulation you're running. Okay, I'll move on to now we're going to start to run ChirpSim and FAST.Farm. Yeah, questions? $50? So most likely it's not going to change much. The turbines, it would probably be exactly the same as this. If I just have a lot of turbines, I just have more rows here, more turbines, right? And this, yeah, time step depends on your chord max, on your diameter, on your frequency max. So it shouldn't be affected. More questions? Yeah. Yeah, it's how to find the delta X and delta T. Yeah, exactly. But the toolbox is going to do it for you. So I'm going to scroll down. I don't think I'm using it right now in that example. I shouldn't have. By default, it's using a random value of 10. Yeah, it kind of need a tiny bit of TI. Yeah. So let's move to example 2, because example 2, all of a sudden we need to give all the input that the object need. No more default value. And we're going to use ChirpSim because we are not going to run LES. It's too complicated. And if I don't have the time to go through the description of all the parameters, but there's a lot of parameters of where the files are going to be, where is my FAST.Farm binary. Sorry, I double click. What is my turbulence intensity? So now there's no default anymore. I'm going to have to, what is my inflow direction? No more default. So at this stage, the ones that have Mac and Linux, you will need FAST.Farm executable and ChirpSim to go. Hopefully you can go as far as possible without it. I try to set up that way. And you need the Roscoe DLL. Okay. We are going to use, so this is where I'm using for, I'm probably going to skip session 2.1 is if you want to do a baseline setup, I gave you this file, FAST.Farm for initial debug. I told you about it. It's a huge domain where you can just put a turbine in it and make sure your OpenFast simulation runs. I didn't mention it above, but we did it together. My advice to you all is try to run OpenFast first, then put it into a massive box. Make sure you're able to run FAST.Farm with a massive box that is super simple, constant inflow. And then you can start going more complicated. That's what this 2.1 is all about. It's showing you this FAST.Farm for initial debug. It's a huge domain where the turbines is in the center. Next thing we need to understand is 2.2. We need template files, right? So that's why I recommend having an OpenFast simulation that works, is because the toolbox is going to take those template files and put it into all kind of directories and duplicate all of your setup. If your template file is for one wind turbine, it's going to copy it. If you have 10 turbines, it's going to generate the 10 input files for the 10 wind turbine. Those are what we call templates. There are two ways to do templates. Right now, I'm giving you the easy option where I just take an FSTF file, sorry, the main input file of FAST.Farm. And the toolbox is going to recognize, okay, this FSTF points to a FST file that points to a DAT file. It's going to understand everything like that. The alternative is you give a list of all the files you need. I need a FSTF file. I need a turbine file for each wind turbine. I need an elastodyne file for each of my elastodyne, aerodyne blade, etc. You need to give every single input file. One thing to note here is the toolbox, so far, it's programmed in a way that it really wants, when you give it a turbine file, it really wants a .t, capital T, to say this is going to change per turbine. And Elastodyne, for instance, is going to change per turbine because you might start the turbine at different azimuthal position, at different rotational speed. Servodyne, the controller is going to be per turbine because we're going to need, as Jason say, a different DLL per turbine. But like I said, I did this for you in the template directory. If you go in the template directory, this is it. You can see I did wt windturbine.t for the fast farm, for the fast file. For the Servodyne file, I did .t already for you. So that otherwise the toolbox is going to shout at you. Anyway, you don't even have to run those. This is just to tell you there's two ways to do it. And now we jump to the case. Yeah, go ahead. Servodyne. Yeah, but then Moordyne sometimes, sometimes not. Hydrodyne sometimes, sometimes not. Yeah.
If you really want to leave your offset, like, Servodyne change. Also the last one.
Right, you want to make the drawing with something.
How long do you want this to last, by the way? Till half past or 45 past, half past?
Yeah, last slide, they're optional.
Okay, sounds good. Okay, so we are 2.3, we start from scratch, it doesn't really matter. This, I'm gonna start giving template files with option 1, which is I give it just an FSTF file. And because you have different Mac, Linux, and Windows, I give it a different path for where the DLL is. And we defined this earlier at the very, very top. And I'm checking that the binary file of FAST.Farm exists, the TURBSIM file exists. This is just small function that I made for this tutorial for you to debug and make sure you get a bunch of OKs, and then you can move on. We go back to exactly the same section as above when we did the discretization. This is just how many turbines I have, where are they, and what are their maximum chord and frequency. So nothing has changed. This is exactly like the previous example. Now I move on to, after the plot of the layouts. Now we start to decide, okay, how long do I want my simulation to be? 120 seconds in that case. This is an optional parameter, but what is the bottom of my domain? Typically we don't want to use 0, so we use 1 meter above the ground. You can use 5 meters depending on how tall your turbines are. And I'm selecting again the polar grid. And this is important if we want to do a lot of simulation. If you want to run a lot of different mean wind speed, different shear, different power law exponent, different turbulence intensity, different inflow angle, you can have arrays of values here. And the toolbox is going to generate all the input files for you for all the different operating conditions. In that case, I just have one operating condition, and you're going to see it's going to be a simple folder. The next example, we're going to do a bunch of operating conditions, and we're going to have a lot of input files. So let's just run this so that the turbine, the class knows about it. Then we switch to discretization parameters. This is the value I more or less got from example 1. I just extended them a bit so that it runs a bit faster. So I run this. And now, finally, I'm ready to prepare my OpenFast input files. So I'm going to call this big class that I told you about. I told you it has 1 million input. The good thing is once, you know, it needs everything to run FAST.Farm. So you can just take this chunk of code and copy paste it each time you need it. I'm going to create an instance of this FAST.Farm case creation. Then we call set template file name, which takes the template files, a couple of functions to calculate some domain sizes, and then it's copying the turbine files for each case. In that case, we only have one case, one wind speed. You can try running this. Hopefully it's going to work for you. Tells you a couple of things, that it has detected which template file to use, and everything is in the template directory. And as Jason mentioned, it creates a copy of the controller for you, of the DLL. And in my case, somehow something, this is great. Do you also have this error? What have I done? libdiscon has been given, but no control input. Lovely. Let me see what's going on. What if I forgot to run something? Okay, well, this is great. If it runs for you, keep going. What happens at this stage is you should have a bunch of input file that has been generated in this folder ff example2 1 sim. Look into this, try to see what this is a new folder that has been created for you. And for me, it is empty, but for you, it shouldn't be. Oh, we're doing example 2 now. Huh? Let's see if my, at least the Python script works. Ah, you know why? Okay, because locally, I know what I did. I turn off, yes. Actually, I should just read the message, tell me something. Remember what I did to you when I said, hey, if your Servodyne doesn't work, kill a Servodyne. And so right now I'm giving a DLL, and the class is not happy because I'm not using Servodyne. Okay, we're good, hopefully. So comp servo equals 1. Great. Okay, I go back here, run again, fingers crossed. Okay. Let's see, I think not yet. This is going to come in the, yeah, terpsim is empty. So we need to generate the input file for terpsim. That's what's coming next. But you can see you have two turbine files, W2, T1 and T2. You can compare them to see, hey, what's difference between those? What is different between those two? Not much. It's just using two different, one is using Elastodyne T1. So they have difference in the Elastodyne and the Servodyne. That's what difference between those. And we can compare those two Elastodyne files if we want to. The only difference is in the azimuth. Somehow the OpenFast toolbox likes to put a random azimuth angle to kind of, to avoid a bit of, to give more stochasticity in your inputs. And two different Servodyne files, and each of them is pointing to a different DLL. And put the absolute path. You have T1.dll, sorry, and T2.dll. That's the main difference. Okay, so that was automatically done by the class. We have one. So this is a very simple example, and when it's a simple example, I pass the argument flat equals true to just say that just means create one directory. If you had when we're gonna have a parametric sweep, we're gonna have a way more complicated directory structure. Okay. Anyway, if you just want to run one case, this is it. We move to 2.4, I think, at this stage, right? We can plot the domain if you want. But it's the same as before, and we move to 2.4. Let's create the terpsim input file. You can run that cell. Hopefully there's nothing that happens, but if you go back to what happened is the terpsim, you have a load of input that has been created. This is a terpsim input file that has the spatial resolution for the full farm. It doesn't have too much grid cells in the Y and Z. It has a delta T equals 2 seconds. You know, it's the low resolution grid that has been created. When we do TurpSim low batch prepare, so TurpSim low because we're dealing with the low res, okay? Batch, it created a batch file and it tells me here it created this batch file. Okay, so you could look at this batch file. If you have Linux, it's going to create .sh. And you can look at the content of the batch file. It's basically getting your TurpSim executable, whatever was in TS bin, and the input file that was generated. So it doesn't hurt. You could try to take your TurpSim file and run it locally. You can try, you know, if you're debugging things, you could nothing. And you don't have to do it. I'm just going to show you how debugging works. You take this TurpSim executable, you go into this TurpSim folder. On Windows, you can just drag and drop the input file. And you have to accept that it's not a virus. It's nothing bad's going to happen. And pretty quickly, boom, I have a BTS file that has been generated. That's the you know, hacky way of doing it manually. You drag and drop it on the executable, or you open a terminal and you run it. If you have my little Python tool, py.view, if you work with FAST.Farm or OpenFast, it's not a bad idea to have py.view. You can download it, install it whenever you have time. You're going to see me using it maybe today. So you can try this tool when you have time. Py.view can open a BTS file and show you the log law. We can see that we have shear. So I have Z here on this axis and the velocity. That's the mean shear. This is a bit of a bug here, but UVW, how does the velocity look at the mean line? You can also do a 2D plot, see how the turbulence look like, and you have some average values. This is a YZ plot. So it's a front view, and you can see we have a linear shear, low velocity at the bottom, high velocity at the top. That's the average velocity. But you can do all kinds. You can look at your turbulence. One thing you can look at, and I don't know why this doesn't show up nicely now, is the cross-correlation velocity, rho UU VVW. Jason mentioned quickly in his talk that when you generate a TurpSim turbulence box, you want the lateral coherence is very important because that's what defines the coherence tells you how your wake meander. If you have no coherence, if a point here and a point at delta Y has no correlation, they're basically noise. So each of them are like shaking completely independently. But if you have a big gust, a big structure, they should, they should move with some coherence between them. And in that case, you can, if you're used to it, you can see that there's some coherence because I think I should have given. I have another example without coherence, and then basically the VV and the W are not as wide. Okay, the peak in the middle would be narrower. Anyway, this was the hacky way to generate the turbulence box. You can try from the, if you're lucky, you can try from the notebook. I don't know if you've tried the next cell. I wonder how many of you make it work. It's the low batch run. I wrote this last week. It's a cute little script that just runs in Jupyter Notebook or any terminal and shows you just like the top lines of whatever is in the terminal. Who has run it and it doesn't work? Will you have a TurpSim that you compiled yourself? Yes, because right now you have a Mac, right? And you need to compile TurpSim. It ships with OpenFast. Maybe Abinit can help you. And then you change your TurpSim to ts.bin at the very top here. TurpSim binary should be the path to the TurpSim that you compiled. Just call it TurpSim. Just write TurpSim here and fingers crossed it works. You can look at whatever the batch file is. Sorry for the scrolling. You can look at what's inside of your batch. Oh, I'm too. Yeah, you batch file, but basically it's about in a terminal. You can also go in there and just right click, open a terminal and do terpsim. If you have terpsim available in your path, you can do terpsim the low dot input and it would run. Moving on, who else is stuck at this stage? I'll move on. So we have our low resolution box. Let's do the high resolution box. 2.5. Again, high setup, high bash prepare. Let's look at what was generated. If I go again in the terpsim folder, I see a high T1.input, high T2.input. You can compare those two. Doesn't hurt. There's only one difference. They're using a different user file for the time series. What does that mean is you can also see there's 2 time series that have been generated here automatically. Those, I think PyDad can plot them as well. It tells you at hub height what is the velocity from the low res. So this is the thing that on your own, it would be impossible to do. Without the toolbox, it would be super difficult. You would have to go into the low.bts file, see where your turbine is, each of your turbines, turbine 1 and turbine 2, find what is the hub height velocity, and put this into a text file like this. This is to make sure the velocity at the turbine is the same, well, is consistent with the low res box. Do everyone understand this, or who has a? It would be difficult to do, right? But so it's everything is done automatically based on the using the toolbox. So someone mentioned that if you already know FAST.Farm pretty well and you want to use a cluster, so I wrote this function high batch prepare, but you can also use the function low slurm prepare, which is if you use slurm, you can give it a template batch file and it tries to do something for you. Then you can submit to your cluster. Okay, so just something you know for the advanced users. You can see now my batch file has 2 lines. It's calling terpsim on the high T1 and terpsim on the high T2. So what I could do, again, I could, instead of I could go here and call terpsim or drag and drop the input file to generate those boxes. I could also look at this file that was generated. That's my batch file that was created. I could double click on it and hopefully it runs, right? It's going to run terpsim for you for each of those input file. Okay, if you need to debug. Otherwise, you can use my function here that runs it in the terminal. So you can run it in the terminal, make sure you get your boxes. High, so it's terpsim high batch run. And at the end of the day, terpsim, you should have high T1.bts, high T2.bts, which are higher resolution file. One thing that I like doing in PyDad view also, I go into file info here. This is my low.bts. It tells me the Z, the spatial resolution in Z, Y, and time resolution. It gives me the ID 8. 8 means periodic, so those files are periodic. And so I can grab also a high T1, and it will have a different time resolution, spatial resolution than the other one. And I think you can see it also in the what am I doing here? UVW. I don't know why PyDad does this to me, but yeah. You can see it's less coarse than the other one. Okay, there's clearly a finer temporal resolution in those high-res boxes. Moving on, let's create the FAST.Farm input file and run FAST.Farm for the first time. So FAST.Farm setup. Again, we generate a batch input file. And let's see what's happening. Before that, now we basically have a new file in the folder, which is ff.fstf. Before it was not here, and that's our main FAST.Farm file. So again, you can grab the FAST.Farm file if you need to debug the FAST.Farm executable, pull it in this folder, and you can drag and drop it, or you could run FAST.Farm like this if you want. And you have two messages because you have two instances of Roscoe that shows up. And it might be a bit slow for you. It is slower than usual for me. One thing to note is the executable I gave you doesn't have OpenMP. That's the one that is shipped with OpenFast on the. You can see it here at the top when I run FAST.Farm. At the very top, the message I get is OpenMP no, which means it's only using one core. Yeah. Yeah, so you would have to go back. The problem is you have to, in that, I don't know where you are. Actually, I've added a new argument in the latest version where you can say here tsbin equals and you give it the path. I don't think that's going to work for you though. That's only in the latest dev version. The alternative is you have to go all the way up here, change your tsbin here. Change tsbin to wherever the path of your TRPSIN. Rerun the FAST.Farm creation that was in 2.2. I know it's a long example. Yeah, you have to rerun 2.3 so that the TRPSIN binary is well accounted for when you give it here. And then then that should work. The FAST.Farm didn't? But you have Windows, right? Yeah, but that's probably different. Yeah. Well, you can always run it manually or yeah, one of the options is going to work. Yeah, you can try to rerun them. So this is just for you if you want to run them in the terminal. You can run that cell here, TS high batch run. But if you've done it my way by drag and dropping, it's probably still running. Are you also stuck here for some of you? Or? Mine is pretty slow. I hope it's not crashing. Sometimes when FAST.Farm it's slow, it's crashing internally. But what we can do at this stage, if it's running, you can see I have a new folder, VTK FAST.Farm. And it's generating a bunch of VTK files in there. We can try to open them in PowerView. If you don't have PowerView, you can try to install it. I'm just going to type it here for you to find it. PowerView. Okay, this is where it's a VTK viewer. So you can visualize the output of FAST.Farm with this. You can open, once you have PowerView open, you can open a FAST.Farm tutorial. We're doing this example 2. And we have a bunch of planes. I'm going to open all of them. Click on 2D, 3D here to make sure we are in 3D view. There's this 2D, 3D thing. And if I press play, I can see the simulation unfolding. And you can see how the simulation is clearly not done. I've made it such that the time step should be long enough that the wake should hit each other. You can just look at maybe this one, the top view. That's the top view case. When the simulation is done, if it ever is, hopefully you'll see those wake planes, the wake planes from the first turbine here hitting the second turbine. Your FAST.Farm is aborting. At what point? Does it tell you why? It's failing. Can you try just the manual way? You take your FAST.Farm executable, you put it here. You can right-click, open a terminal, and just do FAST.Farm ff of FSTF. See if it runs. PowerView is this thing to see the planes. And py.view is for opening the out file and the BTS files. Yeah, no worries. But yeah, PyReview is for the VTK files. Can you raise your hand if you have VTK files? Have you reached that stage? Only 2? You don't, you're far, you're just watching at this stage, you gave up? You got the VTK? Nice. You got them? Good job. Okay. How about you? You? Great. Okay. Let me clean up a bit. It's definitely slower than usual. I think I was in energy saver mode and well, kind of confused of where I am. Okay. Did you run it, Jason? Oh, it's still running? With the X-ray, you're stuck. Yeah, it's a bummer. Yeah, or you can open Anaconda. You have Anaconda, right? You can open an Anaconda prompt. And how about if you do Python.n-m? Or you can do //user also. What's this all about? You can do python.m pip install something. That's usually the best because it chooses the current Python that is in your terminal. And you can also, yeah, I'm putting it on the screen here. You can also do user to say install it for the current user and not admin -- user. Oh, sorry, disappeared. All right, FAST.Farm, do your thing. Anyway, once we are at this stage, it's never a bad idea to debug. So we have a bunch of output files being written at the moment. There's ff.out, which is the FAST.Farm output file, and then we have one for each turbine. fft1.out, fft2.out. So py.view can open those for you. Maybe I'll go one by one, but so the FAST.Farm output file has, for instance, the ambient wind in the X direction for the first turbine and the second turbine. That's the wind in the X direction. You can see the mean is about 8 meters per second. And if I click on reload, you can see that the simulation is still running. It takes time before it reaches still not at 120. We also have very important the rotor thrust at each turbine. Ooh la la. This is slightly concerning. I don't know why it's 0. We have the yaw error of each turbine. What is the misalignment of each turbine? Potentially, you have also the thrust at different nodes along the turbine of turbine 1 and turbine 2. Py.view has a little nodal average function that you can use. So you do OpenFast nodal average, and then you click on average. And in that case, I don't know why my Py.view is crashing today, but it should give you the thrust coefficient for each turbine as function of radius. I know what was going on. Okay. Yeah, I don't know why the other one is 0. Yeah, if you have PyDatView, if you pip install PyDatView, you can launch PyDatView from Jupyter Notebooks, but it's basically the same as opening it like this. Yeah, on the cluster, to debug on clusters is more difficult, right? You need a X, you need a window to be able to visualize things. Yeah. Yeah.
And base file that
Okay, so yeah, always debug your output. Let's look at the turbine output. It's never a bad idea to look at turbine 1, turbine 2, what they are doing. And already the nice thing is now my simulation has gone far enough, I can tell. This is turbine 1, turbine 2. First channel is the wind speed. You can see what's going on here at around 70 seconds. Turbine 2 sees a big drop of wind speed. So my guess now is if I reload the files in ParaView, we can probably see that the wake is hitting the second turbine. Okay, that's what's going on here. The wake is hitting the second turbine. So in PyDatView, I can tell there's a big drop in velocity for turbine 2. You know, always good to do sanity checks like this. We can look at the power, rotor aerodynamic power. You can see there's a big drop in power as soon as the wake hits turbine 2. Not a bad idea to look at the rotor speed as well. The controller is not the best controller in the world for that turbine. I didn't tune it. I think it's kind of slow, but it's varying the rotor speed based on the inflow. It's also doing a bit of pitching as soon as the wake arrives. Yeah. Yeah. Let me see. I don't even think I'm running elastic simulation, to be fair, because I wanted this to run fast. So I think this is probably either tower shadow or pure. I think it's maybe my blade are flexible. It's a good question. Let's just look. I think everything is rigid, so it is purely aerodynamics. I think it comes from the tower shadow passing the tower. That's my guess. Or the shear. The shear is high enough that it's not what? It could be that we're chopping through the wake, but I see it before the wake, so I don't think so. What did you say? Yeah, you can do the math. We have 2 diameters at 8 meters per second. So if the wake we're moving, it's moving slightly slower than the wind speed, right? So you can try to figure out when the wake is going to hit your turbine too. Okay, I think we're almost there. I think it's done. Yeah, the simulation is done. So let's move on with the I think this is basically the end of example 2 now. You could modify here. We give you an example of if you wanted to change your input file, you could change the variable nx low, for instance, to make the domain slightly longer. You can replot your domain after that. Anyway, it creates a batch file that you can run. Right now, I did it from the terminal, but you can do it from the batch file as well. Oh, shoot, I shouldn't have done this. My mistake. Well, you know what? It's running faster now. That's the good thing. But so when that happens, I'm gonna kill everything. I'm gonna kill the kernel and hope that everything goes well. Yeah, I'm just gonna redo everything. It's lovely. Loading the toolbox, setting the binaries. Where is it? This is just too big. By the way, I don't like Jupyter Notebooks. I think it's good for demo and debugging, but it makes you a horrible programmer. So exactly, I just do this for this workshop and that's it. This is an opinion, of course. Everyone can have their own opinion. This is my own. Here I am. Anyway, I think example 2 was almost done anyway. So we have section 2.7 where you can change the input files after they have been created. So it shows you can do a for loop on all the input file, change the aerodyne, change the elastodyne file. It might not even work for me. I jumped around. I'm going to move to example 3 anyway. I think if for the advanced user, you can read section 2.8, how to run on the cluster and generate a bunch of files. And I'm going to move to section 3. Try running first cell. First cell is huge. So it has basically the path to where the files are going to be created. It has our turbines again. The only difference in this case is I didn't put flat equals true. So this is exactly the same as example 2. But it's using the whole folder structure that the class likes to use. If you run example 3, you have FAST.Farm example 3 _ seeds, the folder that shows up. I went a bit too fast, but basically I'm stopping at 3.1. There's a big section with all the inputs. Then I have the FAST.Farm case creation, and that's about all you need to do right now. Just run this FAST.Farm case creation, and it should generate the folder FAST.Farm example 3 _ seeds. In there, you have a folder condition 0. In there, you have seed 0, seed 1, because we have 2 turbulent seeds. That's the difference here. You have a folder case 0. Finally, in that folder, we recognize the same input files as before. Instead of TurpSim, I have seed 0 and seed 1. Each of them have a TurpSim file. So navigate those folders, try to see what's going on. It seems complicated, so that's why we didn't do it for example 2. It's getting you ready for doing parametric sweeps. Imagine you want to do a bunch of wind speed, a bunch of turbulence intensities. Then you need a bunch of TurpSim boxes, right? If you wanted to do the same wind speed, but at different random seeds, different turbulence, you need different, it creates everything in different folders. So in seed 0, I have a low.bts. In seed 1, I have a low.bts that are different. And I think I'm going to try to run that case. At least maybe I'll run it with the batch file. Right now I'm generating the TurpSim file for each of the high res and the low res. Takes a bit of time when you run this cell, but not too bad. Then we set up FAST.Farm. It creates a batch file that has 2 cases, and I would advise you not to run it. Run it separately. So I have a batch file somewhere in example 3 that says run all fastfarm.bat. And what I'm going to do is I'm going to double click on it or run it from the terminal. I'm going to open a terminal. Instead of running it from the Jupyter notebook, because you cannot kill it when it's running in the Jupyter notebook. That's why. So run all fastfarm.bat. It's going to run my 2 FastFarm simulations in the background while we move on. Exactly. So the thing that happened in that setup is I still have only 1 wind speed, but I have number of seeds 2. That's what I forgot. But yeah, number of seeds is 2. So now we have 2. It's going to generate 2 turbulence boxes at the same shear, turbulence intensity, and wind speed. Yeah, because the low res are put there. The low res boxes are here. So this is only the low res, and then in each of the case, because for a given low res, you can do different yaw and keep the same inflow of the low res. So to avoid creating files that are the same, they are placed here. So that's the distinction between condition and cases. Condition is basically the inflow. And case is like, how is my, I don't know, controller? How is my yaw? How is... It does it sequentially. Of course, if you have a cluster, there's also this slurm prepare that it's kind of submitted everywhere to your cluster. But here it does it sequentially. Yeah, your batch file, you can look at it. This run all FAST.Farm has two lines. One line to run this case, and then to run that one. Yeah. If you go into this file, FAST.Farm.fstf, it points to the right low res and the whole, the correct things. I go to this case 0, seed 0. This is actually where my FAST.Farm is. My FAST.Farm input file is under seed 0, and I have a different one under seed 1. So I can compare them. They're actually the same FAST.Farm input file, but different folders. So you can see the difference. Actually, the FAST.Farm is the same, but the terpsim files are different. They point to different inflow. Their time series are different because it's different low res from different seeds. Let's do a more complicated file, but you can see how things get complicated. Right now, we're just doing 2 seeds at the same wind speed. And it's already, well, the folder structure, you kind of get used to it after a while, but if you were to set it up yourself, it would be complicated. Is there questions at this stage? It is advanced and hardcore. So you have the notebook and you can try it at home. At this stage, we're not going to run anything. I'm just going to show you what happens when, so you can just look, okay? There's no need for you to really run at the same time because we're not going to run the simulation. Yeah, and so that's where you're going to need a cluster. And instead of maybe doing the batch, you can try to submit in a cluster instead. But yeah, even running terpsim, those cases are small. But running terpsim for huge domain takes forever, and you might want to do this on the cluster. A first example, if we can gather everyone, if you still have a bit of energy. We have two velocity VHub 8 and 10, 3 inflow directions. We run, it generates all the input file for us. This is where the X array comes in. You have all the conditions into an array that tells you what is my VHub, what is my TI. Anyway, all the cases you have, we don't have too many. We have 3 cases that have different names. It's actually not that interesting at this stage. We can plot the layout. That's what's interesting. This plots all the cases that are behind the scene, and we have 2 different wind speeds, 3 different inflow directions. And when you use terpsim and you change the inflow direction, the OpenFast toolbox is going to rotate your layout. Instead of changing the wind speed direction, it's rotating the turbine, the farm. Okay, so the reason is a limitation of terpsim. So this helps you visualize what's going on behind the scene, and it's doing all of this in the background for you. All the files that has been generated in the background for example 3 wind speed, wind direction. Now you see I have 2 conditions for each wind speed, 8 and 10 meters per second. I have 6 seeds. So there's a lot of things going on in the background for all of this. Let's move on to a different case, yaw misalignment. You can set up the initial yaw of each turbine or each inflow direction. In that case, I have 2 inflow directions, 0 and 35. only one hub velocity. But I'm gonna try for 0 degree, I'm gonna have 0 yaw, and for 35 degrees yaw wind direction, I'm gonna have 10 degrees yaw. That's what this does. Again, this is a bit advanced. This is how all your cases look like. The darker one is like the baseline. I have 0 wind direction and 0 yaw. The second case, I have 35 degrees yaw wind and 10 degrees yaw. It would be a nightmare for you to set this up on your own. So the class is doing this for us. I'm going to move on to post-processing. It's going to use my first example. So hopefully those files exist. If you have run the first example with one simulation, hopefully you can run that cell. You can try it. You can try 4.1 if you have run the first example. Have you run it? No, you don't have X-array, so you couldn't do it. Does anyone can run 4.1 here at this stage? The question is, if you, in your tutorial in one sim, do you have those binary file generated? Basically, that's what we're going to post-process, and a bunch of VTK files. We're going to post-process those. The simplest thing you can do, this is basically what PyDAView does. It uses fast output file from the OpenFast toolbox, reads them, converts them to data frames. So it's a Python thing. That's a table basically, and then you can plot whatever. If I want to plot rotor power as function of time, it's a simple Python plot. You can see it's basically the same as what we had in PyDAView. This is rod power and not rod arrow power. Okay, same as PyDAView. And let's do some other simple. We can just open a VTK file. We don't need PyDAView. We can use this VTK file object and plot the velocity from a VTK file. Okay. This is the code that does this. You can open them all manually and do the average, compute the mean deficit. This is 4.1 basic post-processing. If you want to do more advanced post-processing, it needs my seed one, which I hope I have run. Which I don't think I have run. No, I do have run it. Okay, perfect. That's the one that I run on a separate terminal. So this, some of you are going to get stuck also here because it needs a special package. In my case, I have it. It is going to throw an error at you if you don't have this package. Once again, you do need to do pip install that package. But I'm going to go quickly. Advanced post-processing, basically, it knows all your input files. It knows the location of all your files, and it can try to compute averages for you. And everything is stored in X arrays. So you can select for a given seed, what is the power. Again, I think this you need to look at home when your brain is not too tired. But like you can plot the power for all the cases. It's all like it figures it out. It goes into this X array and finds the right values. It can also average all the FAST.Farm output files, the VTK files. It reads them all in parallel and then can very quickly find the mean the WEG deficit for a given seed. So if you run the example 3 with the seeds, you should be able to run this post-processing stuff. And if you don't want to average them, you can just pick one specific plane and it does it. It is a bit much. Yeah. So you have this feel free to reach out. If you cannot run this at home, you can tell me what error you have and I can help you out. I would say start with basic post-processing, 4.1, and then when you get familiar, maybe do 4.2. What do you say? You don't have the data at the moment, yeah. So really, you can just open the batch file in SIDS and double click on your batch file in SIDS, and that's going to work. You just take this batch file, double click on it, boop, and it's going to run the 2 FAST.Farm simulation for you. You stopped it. Okay. Yeah, I'm going to stop here. Do you have questions? Yeah. Yeah, this gets difficult when you run a lot of them. So this is where the first examples, like running them one by one in the terminal, you need to understand what's behind the batch script. So if your output file is missing from some simulation, you can try to rerun those simulations manually, like FAST.Farm with the FST file. Yeah, that's pausing and doesn't really, it happens in the terminal on Windows. When you click enter, it pauses it sometimes. But I don't recommend it because then you don't understand why the simulations stop working. So yeah, just
Read that about
Yeah.
the checkpoint restart capability. Yeah, there's some documentation about it before. Like, the cluster died, what we want to restart.
I don't know anyone that does it though. Only the CFD people do checkpoints when they do CFD with OpenFast. But in FAST.Farm, it's cheap enough that you just rerun it. Do you want to cover some slides? I know they're pretty burnt out.
Switch this one.
Yeah, that'd be great.
Any more questions for Manuel before he has to take off the airport?
Yeah, my email, you'll find it, or hopefully you can find me on LinkedIn or something and just shoot me an email if you're stuck. And Jason has some finishing remarks. So.